Hello everyone, George here again, and now we're going to talk about loops. This is a very interesting concept in programming, so I bet we'll have fun. We'll have fun in the next probably 2 hours because this is a long subject, but bear with me, stay with me, try to think, that's the most important thing. Try to sketch up things while we're doing this whole thing, and you'll be fine, and you'll learn a great new concept in programming. So again, before we start with the real stuff, again I'm warning you, as I warned you in the past video about conditional statements, this is actually a home recording because the actual recording got broken. The actual recording was 1 year ago, so now we're recovering these. You can learn more about what happened actually. You can't actually learn more about what happened, but I said this in the last video, so I'm repeating it again. So any ambient sounds, anything that doesn't seem right, yeah, blame it on the fact that I'm recording from home. There's no audience, so sorry, can't answer questions, but you can always ask your questions at the comments section below the video, and you can find the materials in the description below the video again. So we started our recording, and we're going to talk about loops, a very interesting concept in programming. First of all, we're going to talk about what a loop is, how it functions, and what kind of loops there are in C#. So now to mention, loops are a concept in programming, not only in C#. We're studying fundamentals of programming here, not only of the language C#, we're studying it through the language C#. So now we'll see what while, do while, and for loops are, and we'll make analogies to other programming languages which use the same types of loops. Then we'll speak about a for each loop, which is a special loop in C#, and then we'll discuss the special loop operators, the so-called jump operators, which basically jump through code. Now goto isn't really a jump operator, isn't really a loop operator, but still it's something worth mentioning and not worth using. But we'll talk about that later on. Then we'll talk about nested loops. In the previous video we talked about nested if statements. Now we'll talk about nested loops, and you'll see it's basically the same thing. So what, pray tell, is a loop? Well, a loop is some sort of statement which allows you to repeat the execution of block of statements. Basically, I just read the first sentence in my slide. So more descriptively, a loop is something that allows you to programmatically repeat code. Now, and up until now, before you heard the concept of loops, before you learn what a loop is, you probably, if you wanted to repeat the execution of a piece of code, you basically repeated that code. You copy-pasted that code and you had repeated execution. Now, because in some cases we don't know how much times we need to repeat some execution of some code, and because some problems really require traversing and repeating one action with different parameters in different situations a different number of times, this is achieved through loops in programming. Now, a loop is something which takes information about conditions on when to execute a piece of code and eventually how many times to execute. Now we'll see four different kinds of loops. Generally, loops either execute some code a fixed number of times, that is, for example, 5 times, 10 times, 25 times, 1 billion times, and so on. Execute code while some given condition holds. So, for example, you already saw the if statement. Well, the if statement executes code once, exactly once, when a condition is met. Well, some loops execute code not once, but while a condition holds. Basically, such a loop could end when its body eventually modifies the condition or leads the program into a state in which state that condition no longer holds. For example, game is running and a while loop we'll see what a while loop is. But a while loop which executes basically each and every turn of the game until the number of turns, or until, for example, all of the enemies are killed or destroyed, or all of the good guys are killed or destroyed, or something like that. That leads into a state where the game shouldn't continue, and then the game is running variable, boolean variable, will be set to false, and so the loop will stop executing. We'll talk about what I mean in a few moments. So even if you got lost there, you'll get found again. So another thing you can achieve with loops is traverse each and every element of a collection and execute some particular code on each and every element of a collection. Now, what a collection is, we haven't really talked about that in the videos so far, but the collection is basically what you expect: a group of variables of the same type generally, which are grouped in a bigger variable. Imagine it like that. So a collection of books, for example. We do a for each loop, we'll talk about that, on each and every element of a collection of books. And for example, you don't know, read that book, or whatever, or throw it in the cache, the trash, not in the cache. You can't throw a book in the cache. Actually, you can if you have a lot of cache, but that's a whole nother subject. So what happens if a loop has a condition which ties it to run infinitely? Well, we call that an infinite loop. So basically you can have a loop which never ends. So your computer executes a program which doesn't do, or does the same thing over and over again infinitely. That's possible. That's part of the reason why you've seen programs hang. I mean, you have a program, it works, and suddenly it seems to have stopped working. Actually, it hasn't, or in most cases it hasn't stopped working, but it has fallen into an infinite loop, which is, for example, calculating something, and that program can't, while it is calculating that stuff, it can't find the time to turn back to your operating system and say, hey, I'm alive, don't switch me off. And that's why you get the don't send, because that program never says I'm alive, and your operating system, for example Windows or whatever you're using, says, oops, this thing crashed. It's not responding. Actually, that it doesn't say crashed, it says this thing isn't responding. So no matter about that. Now, what are loops? Sorry about that. The most basic sort of loop, not the most simple one, but the most basic sort of loop is the so-called while loop. It's the same thing as an if statement, exactly the same thing. It's written down exactly the same way, only that it's not if, it's while. And the only difference is that an if statement checks the condition, and if the condition is met, then it executes the code into its body, and then goes on with the normal execution of the program. It passes on the control to the normal lines of code, to the method that called the if statement. The while loop doesn't do that. The while loop checks if the condition is met, and then executes the code in its body. After it executes the code in its body, it again checks if the condition holds and repeats the execution of the body. And while, that's where its name comes from, while that condition is met, the statements in that while body will be executed. So basically what happens is the program goes to here. It says it sees a while loop. Cool. Okay, now we're going to check a condition, much like an if statement does. Okay, check the condition. If the condition is true, go into here and start executing these statements. These statements can be a lot. There can be 1, 2, 3, 20, 2 billion, whatever quantity you want. Some statements, any sort of statements. These statements can be called, they can be, for example, initialization of variables. They can be declaring of variables. They can be catching exceptions, error handling, if-else statements, nested if-else statements, other loops also. That's what we would call nested loops further into this lecture, and so on. Everything you wish, everything you can have outside a while loop you can have inside a while loop, including other while loops. So it checks the condition and starts executing these statements. When it's finished executing all of the statements, it goes back to the condition, basically goes back to this while thing, and checks the condition again. If the condition still holds, if the condition is still true, if this thing is true, it continues with the statements. So goes into this loop body and executes all of the statements, absolutely all of them, again. Okay, and then checks back the condition and executes all of the statements and so on. There's only one or two cases in which not all of the statements can be executed. Those are the jump operators, break, go to, continue, or the return operator, but we'll discuss those in a moment. Okay, so basically what happens is, what you need to know at this stage is that it executes each and every statement and then goes back to checking the condition. First checks at the first time when the program reaches a while, it checks the condition, then does the statements, then checks the condition, then does the statements, and so on. That's so long as the condition holds. That's where the while word comes from. While the condition, do the statements. Okay, so this thing over here is the body. As we discussed in the chapter regarding if-else statements, conditional statements, bodies are things which enclose statements, things which enclose operations, which are related to some sort of conditional or some sort of loop. So basically what we're saying here is, if you want to have multiple operations executed each time the condition of a given loop holds, well, you want to put those statements, those operations, in brackets, in curly brackets, which are called the body of this while loop. So of course, if you want only one operation, you can go without these brackets. That is only one operation. For example, plus. I don't know why I wrote it that way, but this is one operation, and you don't have anything here. Now you could do this, but as we said in the conditional statements video, this is not a good idea. We discussed what isn't a good idea, mainly because it's easy to make mistakes this way. So always use these brackets, absolutely always. No, it doesn't matter if you have only one statement. Again, use brackets always. Just take it as a universal truth. Always use brackets in programming everywhere you can. It makes code a lot clearer. Okay, so if you want a more detailed description of why to use brackets, see the last video, conditional statements. And now we're going to continue on with this thing. So the condition, as in if statements, as in conditional statements, is you guessed it, Boolean variable. Okay, so that Boolean variable or Boolean expression, that's also possible, is always evaluated, and it gets either true or false as a value. So if it is true, these are executed, and we go back to the check. If it is false, we just jump out of the loop and never check this thing again. Okay, so this is also called a loop condition in some cases. Here's how a while loop works. You have the condition over here, seemingly like an if statement. If the condition isn't met, if the condition is false, we jump out of the loop. That is, we go out of the execution, much like in an if statement. The only difference is, if the condition is true, we execute all the statements in that while. So if we have while brackets condition, and then we have curly brackets and statements in them, after we execute those statements, we go back. We don't go forward, we go back. And when that condition, if that condition still holds, we again execute those statements. So we fall into a loop. We'll see how we turn around over here, and then here, and then here, and we loop around. We loop in these two things while this condition is true. At the moment at which it becomes false, if such a moment comes, we continue with the normal execution of the program. We leave the loop. We exit the loop. That's the standard terminology is we exit the loop, or we leave the loop, or we stop looping, or we stop iterating. Executing a single execution of the statement is called an iteration. So one check of the condition. After the check of the condition, if it is true, we will do an iteration of these statements. That basically meaning we will repeat these statements for the first time. So we will do them the first time. Then if the condition is still true, we will iterate again. Iterate means repeat, or whatever you like to translate it to in your language or understand it in your brain. So we call this an iteration. One execution of all the statements is called an iteration. And that's standard terminology for loops, so you know in the future how things work. So here we have a while loop which counts. So sorry about that. What does it count? Well, it counts the numbers from 0 to 9. How does it work? Well, we have a counter variable which starts from 0. You see this value 0. Okay, so we say while the counter variable is less than 10. You know that this is a Boolean expression. You know that it returns either true or false. The counter either is less than 10 or is equal to or greater than 10. So this is a Boolean variable, and what happens? Okay, the first time counter is 0. Well, that's pretty obvious. So 0, which means that this condition is true. Then we will get into this code, execute this console write line, which prints the counter on the console and puts a number prefix before it, and then increases the counter. At this point, after all of these operations finish, we will return to the loop condition. Not in the middle of these operations, not here, but after all of them finish. So yeah, actually here, because this is the last operation. But if this was the other way around, the check would be at the end. Basically when we reach this bracket, we go back here, we check back here. So when we check back here, the first time we had 0. Now we have 1 for counter. This is still true. And we will go in here, print 1 on the console and increase. Counter now becomes 2 over here. Becomes 2, and here we will check, is it less than 10? Well, 2 is less than 10, and so on and so on. This continues until we reach 9. We reach 9, the number 9. Superb. We go here, we print 9 on the console, then we say counter plus plus. At that point, counter becomes 9, and then we go back to that check which says, is counter, which is now 10, sorry, here we don't get 9, sorry about that, we get 10, because 9 plus 1, this 9, plus 1 plus plus is 10. We get 10. Is 10 smaller than 10? Here we have 10. Is 10 smaller than 10? Well, obviously it isn't, so this condition doesn't hold anymore. So because this condition doesn't hold, we will jump out. This condition is wrong, so we will jump out of the loop and continue with the normal execution of the code and continue basically after this bracket. That's what happens in a while loop, and this is how the output would look. Number 0 is 0, number 1, number 2, number 3, and so on up until 9. We won't print out 10. As you saw, we have 9 over here at some point in time. We print out 9, so this outputs to the console 9. Then we have counter plus plus, which makes 9 into 10, but we don't have a print after that. We don't have console write line after that. We had it before that. And the check will happen before console write line is able to happen. So here we will have 10 less than 10, which isn't true, and we will exit without printing the last number. So keep that in mind. Basically the hardest thing to understand about for loops is when they end and when they start. That's once you've got a hang of that, everything else should be easy. The general case should be easy. So the border cases are the most difficult now. In this case, 0 and 9 will be the most difficult to predict, you know, when the loop will end. But if you keep understanding things the way I just basically drew a few seconds ago, well, you won't have any problems. So some examples with the while loop. Sorry, not what I meant to do. Examples of a while loop. Well, imagine you want to calculate the sum of the first n numbers in the natural numbers. That's 1, 2, 3, 4, and so on. Okay, so how do you calculate that sum? Well, basically read a number from the console. You know that should be pretty obvious by now. And what do? We make this is the counter variable which we saw in the last example. You imagine this is the counter, that's what we will use it for. Actually it's called number at the moment because we will use it for the current number we are summing in the sum of 1 to n. Okay, so we make another variable which is the sum. Here we will accumulate the sum which we have reached for the current iteration. So at the beginning the sum is 1 because obviously the sum of one number which has a value of 1 is 1. Then these printouts, ignore them for now, I'll explain later what they do. So ignore this, and ignore this. Okay, maybe not ignore the last. This is just a printout of the sum itself. So what we have here is check if the number which we've reached at the current iteration is less than n. We're going to make the sum of 1 to n inclusively. Now how are we going to do that? Well, we're going to do the following things. We got the number, we got the sum, they're both 1. Then we say number plus plus, so increase number with 1. Number here becomes 2, it becomes the number 2. Then we say sum at number, so add number, the number variable, to sum. So sum at this point in time has the value of what? Well, you guessed it, 1 plus 2 is 3. Okay, now we go back to the number less than n. Now n we don't know at this point in time, but when we're compiling, but when we input it from the console we'll know it. For example, let's say that n is 6. N is 6, that was input from the console. Okay, so here we will always check if number is less than 6. So here the check will be less than, and some color, green for example, 6. Because 6 is a green number, I don't know why, don't ask me. Okay, so sum is 3, number is 2. The yellow thing is, this is green. So the yellow thing is number, the red thing is sum, and the green thing is n. Okay, so number is 2. Here it is 2. Is it smaller than 6? Well, obviously it is. So we continue on here, and number becomes number plus plus, 2 plus plus becomes 3. The number 3. Okay, sum plus equals number, 3 plus 3 will become 6. Sum is 3, sum is 6, number is 3. Go back to check, so we go back here and we make the check. What is the check? Well, the check is 3 smaller than 6? And so on and so on and so on until we reach 5. We reach the number 5. For example, we've reached it over here at some point in time in the future. We've accumulated some sum. I'm not going to calculate it now. If you wish, calculate it. Okay, we've reached the number 5. Then we get number plus plus. Actually, we have 5 here. Is 5 less than 6? Checking this condition. Well, it is. If it is, go to number plus plus. Now here at this line, at this number plus plus line, number becomes 6. Now this condition, number less than n, won't be checked now. It will be checked after all of the statements in this while loop are executed. So let's clear this up a little. N is 6. Number is 5. We check the condition. Is 5 less than 6? Yes. Because it is less than 6, we go into these statements. We will execute all of the statements before we go to the condition check again. So number plus plus, number becomes 6, and we continue with these lines. We don't check the condition now. We will check it later when all of the statements end. Then we accumulate that number in the sum with these lines, and then say check the condition again. After this line of code, before we reach the end, we go back and say, well, is number now, which number now is 6, not 5, is number now less than 6? Is 6 less than 6? Well, obviously no. This is not true anymore, and we exit the loop. So because this condition no longer holds, is no longer met, we leave the loop, because this loop happens while the condition holds. And we go to this line, because this is the line exactly after the loop, because this is the loop's body ending, and this is the line after it. And what do we have here? We'll print the sum. Now, the other console writes, which you see this, console write the sum 1, and then plus some number, and then equals to sum. This will just make so we print out the entire sum. How do we do that? Well, we do that in the following way. The first time we print the sum 1, and then start doing stuff here, and then say print out plus the symbol plus, not adding, just plus, and then the number which we've reached at the moment, this number. So at this moment the number is what? First it was 1, that's why we print here 1. Then number here becomes 2, so we will print 2. So this will become the sum 1, then plus 2, and then this thing will loop around. Number will become 3, and then we will have the sum plus 3, so the sum 1 plus 2 plus 3, and so on. And this will continue until we reach 6. You can write it down and check it the way we wrote down this loop, in the same way, and you can check what you get. And at the end we will place 1 equals the sum which we've accumulated. So that's how you calculate the sum of the first n numbers. Here's an example. Here's sum 1 to n. We enlarge this thing, and here we read something from the console, that's our number n, and we start from 1 for number and 1 for sum. We write down the sum of 1 plus something is something, and while the number is less than n, we do those things which we already discussed. That is basically the exact same code which we saw a moment ago. So now we can see how it works. Initialize this, give me the sum of the first 3 numbers. The sum of the first 3 numbers, which are 1, 2 and 3, is 6. Well, that's basically it. So we can do the same thing. For example, if we start and write down 1, guess what will happen? The sum of 1 is 1. Why? Because this loop never executed. Why didn't it execute? Well, because number is 1, and if n is 1, the condition 1 less than 1 is never true. This is always false, and because this is false, we jump out of the loop directly. So we don't execute, we don't iterate, we just print out the result, and we have the result, which is 1. Okay, and now if we write a bigger number, for example 100, we should get 5050, which is exactly what we did get, 5050. That's a cool riddle. What's the sum of the first 100 numbers? Well, it's 5050. You can calculate it in another way. Of course, that this isn't the optimal way to calculate the sum of the first 10 numbers. There's a mathematical formula which can give you that. But here we're learning how to use loops, and we'll learn how to use them for problems which mathematical formulas cannot solve. But we'll do that in a while, not right now. So that's the problem, that's the example. I explained it already to you, so we won't poke around this anymore. I'll leave poking around to you, so you have what to amuse yourselves with. So another example of using while loops for solving problems, checking whether a prime number, whether a number is prime or not. So basically, what a prime number is a number which divides only by itself and by 1. All other divisions for it have some remainder. So how do we check if a number is prime or not? Well, we obviously I'm starting to mess up my tongue now. We obviously get that number from somewhere, for example the console. Then we create the divider. We'll see what that is going to be used. This is the counter which we will use. As you see, I'm using the term counter a lot of times, and that is because in loops there will generally be some sort of indicator of tracker of your progress. What I mean by that is, well, you will have one variable upon which the execution of the loop will depend. Like here, for example, we have while divider is less than max divider. We'll see what that does in a moment. So what else do we need when we're checking if a number is prime or not? Well, several things. First, after the divider, we need to get the max divider. Now, by what are we going to divide at most when we're checking whether a number is prime or not? Well, if you think about it, we need to check to the square root of the number. Why? Why is that? Well, because if a number is prime, or more like if a number isn't prime, it should be divisible by something that's less than its square root, or at least something that's equal to its square root. For example, take the number 25. It's divisible exactly by its square root and by no other numbers except 1 and 25 themselves. So why do I say that something should be divisible either by its square root or something less than its square root? Because if it's divisible by it can't be divisible by things that are only larger than its square root. Why? Well, for example, if 25 was divisible by something larger than its square, for example, let's take another number. Let's take 27. It's divisible by 3 and 9, obviously, because 3 times 9 makes 27. Well, it can't be dividable only by things larger than its square root, because if you divide it by something larger than its square root, you should get something smaller than its square root, because if you get something larger than its square root, well, obviously the square root of a number multiplied by itself gives the number exactly. Well, if you divide it by something larger than the square root, you can't get something larger again than the square root, because the multiplication of those two should be larger than the number itself. Not sure if you understand what I meant fully, but basically when you check for a prime number, you need to check up until its square root. Every number is either divisible by its square root or by a number smaller than its square root, which when we divide it by that number, we get the number larger than its square root. So we only need to check up to here. You can pause and rewind the video if you want to hear this a few more times, but I hope you understood. If you didn't, well, take it as granted, or search around Google. Okay, another thing we need, so this is the last thing we're going to divide by. This is the first thing which we're going to divide by. Now why not by 1? Well, because everything is divisible by 1. We don't care about that. We care to check the number, whether that number divides by any number between 2 and its maximum divider, which is its square root, and that square root truncated to an integer, that is converted to an integer and its fraction part forgotten. So basically it's integer square root, if it has any. Okay, and we need one more thing, which is a variable prime, which is, well, this number is prime until I've proved wrong. So we take any number in the world as prime. That's logical, you know. How do you prove that the number is not prime? Well, you have to find the divider. If you don't find the divider, that means that it stays prime. So we create a Boolean variable which is named is prime, and we set it to true. We say that every number in the world is prime until proven otherwise, until proven guilty. So we say while the number is prime, and at the same time the control variable of the loop, that divider thing, the counter or whatever you want to call it, is less than max divider, because we don't need to continue further than this, because we explained why the maximum divider of a number could be its square root. So then we start going through each and every number, and for each and every divider possible for that number, you know, this goes from 2 to max divider, which is square root of our number, of this thing, square root of number. So each and every divider possible from 2, 3, 4, 5, 6 and so on up until the square root of number, for each and every divider we will divide number by that divider and check the remainder of the division. If the remainder of the division is exactly 0, then we have a non-prime number. That means we managed to divide the number to some other number which is not 1 or not the number, which breaks the definition of a prime number. So this thing is no longer prime. And we make the Boolean variable prime equal to false. Why? Well, because obviously this thing is no longer prime. And then we increase the divider. At the time when this thing becomes false, if it becomes false, we will go back to this check and we'll see if prime. No, it isn't, because this thing is now false, because the if conditional was executed, because this found a divider. So because this thing is false, the rest of the expression doesn't matter, because in a case where we have the AND operator, if one of the operands of the AND operator is false, everything, the entire expression is false. It's just like the OR operator, where if something is true, doesn't matter which one of them, if this is true, then the entire thing is true, where, well, at the AND operator is exactly the opposite. If one thing is false, then the entire thing is false. So we reach the moment when this thing is false, and we no longer execute the loop, and we just print out the result. Whether now in this case we said that, for example, we reached a false condition, you know, a condition in which number divides by some divider from 2 to its square root. So the number is no longer prime, no longer considered prime, and we print out prime and false. Now, if this thing never happens, which is possible, for example, for number 13, you won't find any divider which gives a remainder of 0. This thing will never happen, but at some point in time, because divider increases each time, divider will become the square root, the max divider of the number. For example, for 13, this would be 3, because 3 times 3 is 9 and 4 times 4 is 16, so 13 is somewhere in the middle, and that thing, when casted to an integer, will become, that is 3 point something, but 3 point something casted to an integer will become 3. So here we will check less than 3, and divider will become 3 less than 3. This is okay, this is still true, but at some point in time, at the next iteration, divider will become 4, and we'll have 4 less than or equal to 3, which is no longer true. This is false, and we will exit the loop and go here and say, is it prime? Well, because we never got into this thing, because this was never true for 13, then we will print out prime, question mark, true. And now we will see this in action. Hope you got the idea of how this thing should work. Again, bear with me, it's a bit difficult for the first time, but if you listen to this enough times and if you try to write it down while you're listening, well, you probably get the idea. So here's our demo, the same code which we discussed up until now. We start it and we say n equals, for example, 14, and we have a common problem, which is I didn't set up my startup project. So I go to Solution Explorer, see the sum of 1 to n is still the active project, and now I'm going to set is prime to the active project with set startup project. Control F4 I pressed. I didn't want to press that. Open this prime again. Control F5. Here's our code. And enter a positive integer number. 14. It's not what? Yeah, it's not prime, sorry. It's not prime because 14 divides by 2. What happened? Well, somewhere here at the first iteration, because divider is at the beginning 2, we get number percent divider, or give me the remainder of number divided by divider, which when we have 14 and 2 will give us exactly 0, because 14 is divisible by 2. Okay, and we got prime equals false. This thing increased, and we got back to the check, and the check said, is it prime? Well, because this thing executed, this will be false, and we terminate our loop. Okay, say we input some other number, for example 9, we get, is this thing prime? Well, no, because we got to the divider, which is 3. is 3, which we checked 3, is this thing less than max divisor? What is max divisor for 9? Well, square root of 9 is exactly 3. So is 3 less than or equal to 3? Well, obviously yes, because we have equal to. And we will check at some point in time, is 9 divisible by 3? And this thing will give us 0, which will make prime false, and then when we go back to this check, this will be false, and the loop will terminate, and then we'll go to this console write line. Okay, so what happens if we have, for example, 17? This is a prime number, because we go from what is the square root of 17? Well, 4 point something. Cast it to an integer, it's 4, so max divisor is 4. We start with divisor less than or equal to 4, and this goes from 2, 3, 4. 70 divided by 2, 3, or 4 never gives us 0. That is, the remainder of the division is never 0. So we will never come into this line of code. This will not execute. Only this will execute. At some point in time, this divisor will become 5. It will be 4 and less than max divisor, which is 4, and then one iteration after that, this will be 5 and this will be 4. This loop will stop because this is no longer true, and we will print that this thing is prime, because prime never changed to false. Now we have a condition here, and we have a boolean variable here, and we use them in unison. We use them symbiotically. They help each other out. So hope you understood that at least partially. Again, if you're having trouble at the moment which you start writing down stuff, it will be much easier. For example, imagine you're a compiler, you're a computer. Start executing each and every line of the code. I basically did that already for you, but you can do it for yourself and you'll understand it much better. Okay, moving on. Closing these windows, I don't need that anymore, and continuing on. Okay, no, sorry, started speaking in Bulgarian. So that's well, you just learned a word in Bulgarian. So means taka. So we have our main method here, and we're going to see the break operator. Now, what the break operator does is it terminates the execution of the innermost loop in which it resides. So this break operator here will stop the execution of this while loop. We'll see what that means just in a second. So we read an integer, and we're going to calculate the factorial, that is the multiplication of the numbers from 1 to n, where n is a number which we input from the console. So we're going to calculate the factorial of n. We start with a result of 1. So the result at the beginning is exactly 1. Now here we have something which looks like a so-called infinite loop. While true, this says while this condition is true, while this is true, while true is true, execute something. Well, this will obviously always execute. So there's nothing which can turn true into false. So this loop should never stop unless there's a break operator in it, or a return operator, or something else of that sort. So what happens here? We have the result of 1. We start and we continue until n becomes 1. We start with n as a number which we input from the console, and each time in which we pass through this loop, we check if n is 1, and if n is 1 we break, because we don't need to multiply by 1 obviously. How do we calculate the factorial of n, which is written down over here? Well, it's perfectly reasonable to say that this thing, n factorial, let's write it in another way. Factorial of n is equal to n multiplied by n minus 1 multiplied by so on, and then multiplied by 3 multiplied by 2. And do we need to multiply it by 1? Well, obviously this thing and this thing is exactly the same, because multiplication by 1 leaves the same number. So it's perfectly sufficient to leave this as is. So basically that's what we're doing here. We're decreasing n each time, we're multiplying it in result, and we're checking whether it becomes 1. Now, while we're multiplying it in result, which is initially 1 actually, so we can fill up something, we multiply by n. So first time result is n. We're going to write this down, the entire thing. So first time, and for example we put in 5. So we have, is 5 equal to 1? No, obviously not. So this thing won't execute. Now here you see a bad example of formatting code. This thing should be in brackets. Even though this code is correct, it will work the exactly same way. This is a bad example of formatting code because it will look weird. You know, you won't be able to read that this thing executes on its own. Always put brackets. We've discussed this already. Now why is our example with bad formatting? Because we have limited space on the slide. So that's why in some places you see a lack of brackets. But don't be fooled by them. They should be there. As you see in the live demo, which we'll show you in a moment, they will be there. The normal brackets will be there. So continuing count. Is 5 less than, if is 5 equal than 1 equal to 1. Here we input 5. Is 5 equal to 1? Well, obviously not. Result multiplied by 5. Result is now 5. And n is now 5. N is 5. And our result is 5. Okay, n minus minus. At this point in time, n becomes 4. Then, is 4 equal to 1? Well, obviously not. So multiply result by 5. 5 multiplied by 4. Then n minus minus. At this point in time, n becomes 3. And so on. At some point in time, n will become 1. Or actually, let's say n will become 2. Yeah, we just wrote it down, the entire thing. Is 2 equal to 1? Well, obviously not. So we multiply result. Here we had by 3, and here we have by 2. Then we say n minus minus again, which makes our n equal to 1. Then we go back to this loop. Now I didn't check the loop condition every time because it's obviously true, and this will execute no matter what. But then we reach this if statement, which almost got disappeared due to my sketching. So now in this situation we have, is n equal to 1? Well, because n last became 1, we have 1 equal to 1, and in this case we have a break. Now break, what it's going to do is going to say exit without executing any other line of code in that loop. So any lines below this break will not be executed. Basically this breaks the loop where it is. Exactly at this point no other statement will be executed, no matter where that statement is. It could be, even if there were brackets here and there was a statement over here in the brackets, this would not be executed. Everything after this break operator will not be executed when it happens, if it happens. When does it happen here? Well, it happens when n is exactly equal to 1. And as we described, we will actually, with this code, we will actually make n multiplied by n minus 1 multiplied by n minus 2, and so on, until we reach 1. At that point we won't do a multiplication because we do not need to. And then we'll print out that the factorial of n is exactly the result which we've accumulated here, because each time we decrease n. Hope you understood that, and here we have a live demo. We open that demo, a factorial with break. Now the real purpose of this demo is to demonstrate that we can have an infinite loop, or a loop that seems infinite, and make it stop. Now what I'm doing here is setting my current selection of a project, of a file, to the startup project. So when I open a file, this project will run. I won't have to make it a startup project each and every time. So we start an infinite loop. Of course we could try to think of a condition in which we should stop. For example, we could just say if n equals to 1, if n is different than 1, n is different than 1, then execute the loop. In other cases, just stop. In the case where n is equal to 1, stop and don't execute anything here. It will be the same thing as this break. Now, generally it's better to make a condition in the while loop than to make an infinite loop. It's better from a coder's point of view, from code readability point of view. But in some cases it will be easier to make a break statement in an infinite loop, so you have to be prepared for that too. So what we do here, well, we obviously make a loop. We use a decimal here to calculate, and we say multiply the factorial by n, and then we decrease n every time. Okay, so at the point where n becomes 1, we do a break, and that will exit all of the lines of the loop. Nothing from here on will be executed. Everything from here on will start being executed at the point where this break initializes. So break basically means get out of here and go to the end of the loop, after the end of the loop actually. That's what a break does. Okay, so start this thing. N is, for example, 5, and this is 120. Now how do we do that cool printing stuff? Well, nothing too fancy, nothing too complicated. We just print n every time in which we iterate through the loop, and after we do the check for is it equal to 1, we print the multiplication. Because if we do the multiplication over here, exactly after the n, guess what will happen? Yeah, we'll have a multiplication sign after the 1 here. See, 5, and we have a multiplication sign after the number 1, which we don't need. So that's why, if we don't need to multiply anymore, we don't need to do these things anymore, then we don't print that multiplication sign because it's unneeded. Okay, so as you saw, this works. I explained how it does work. Now something you'll notice, if we write down 20, it still works, but if we write down 100, it stops working. Why does it stop working? Because the decimal type always has a check which says, does this thing overflow? Now an overflow is trying to save a larger number than a type can hold. That is, decimal can hold 128-bit numbers. Those are pretty large numbers, but still it cannot hold the factorial of the numbers from 1 to 100, and that's why decimal isn't the best type for calculating factorial. It's one of the best types if you want to calculate money, but not when you want to calculate factorial, because it's pretty damn large. What you can use to calculate factorial effectively is a data type called big integer. Now I don't see it at the moment, but I have to include some namespaces. Control dot, yeah, still can't see it. Why can't I see it? Because big integer is a type which is supported from .NET 4.0 onward. So in these projects here I don't have .NET 4.0 because these examples were made long ago where .NET was only up to 2.0. So of course I have them on my I have the DLLs on my computer, so I can add them from references, add reference, and this you can do with any other library which you download as a DLL. So assemblies, and I'm looking for system numerics. Come on, man. I need system numerics. Why don't you find system numerics? Okay, system. Oh yeah, another problem. As I said, this project is .NET 2.0, so it can't find those DLLs. It can't find them in assemblies. If I know where the DLL is, I can find it, but since I don't, I'm going to go to properties over here and convert this project from .NET 2.0 to .NET 4. Yes, I want to close the projects and open them again. And this converted my project to .NET 4.0. Now, here's my factorial again, and now I can say control dot, still not there. So I will add my reference now, add reference, and now I'm going to search for numerics. Come on, why don't you find it? Factorial break. Did I set it to the proper project? Yeah. .NET framework, console application, factorial break. Not sure what's going wrong. No, I don't want to change anything. Oh, this is probably the factorial break project with the factorial C#. I'm probably doing something very stupid right now, and I'm not realizing that I'm doing it. But nonetheless, okay, add reference, and I'm looking for assemblies, and I'm looking for system numerics. There it is. I'm not sure why I didn't find it. Okay, if I write numerics, yeah, it found it now. Not sure why I didn't find it immediately. Maybe it couldn't refresh. Okay, so I press OK. This added a reference to system numerics DLL. That's the library which gives me numerics capabilities, and now I can press Control plus dot, or right click and resolve and click using system numerics, which just adds a reference over here. And then we have this big integer class. Now big integer is a slow mathematical class which could store huge pieces of data. So if I compile this and write down 100, this calculated. You saw that it calculated it a bit slower than other data types because it works in a different way, but in this number you can save, well, basically a number big enough to fill up your entire RAM memory. Not only 128 bits, but as much as you want to. Okay, so that's big integer if you want to save really big numbers, but keep in mind that this thing works pretty damn slow. So pretty damn large numbers, but pretty damn slow. So be careful with that. Okay, now do while loops, but I'm going to take a quick break now, and you won't realize the break actually. So coming back in just 1 second. Now back on the track, we're talking about do while loops. Now do while loop, that this thing is basically the same as a while loop with only one major difference, and that difference is the do. Not the keyword, but the fact that it does the statements and then checks for the condition. Now you might say not very smart, but in some cases you would want to do something, basically to do something at least once and then check for the condition whether to continue doing it. So a do while loop is perfect when you want to execute a group of statements and then based on some condition continue executing. So execute once, and if the condition holds, execute them again, and if the condition continues to hold, then execute them again and again and again, and so on. So that's a do while loop. So basically, if you make the comparison with a while loop could execute 0 times. That's possible. A while loop could, there are situations in which a standard while loop min executions is 0, while a do while loop min executions or iterations or whatever you want to call them is 1. A do while loop will always execute at least once. Basically, making a do while loop is like writing statements, whatever they are, then while condition, and then statements again. That's a do while. But what's the benefit of using a do while? Well, if you need to do something like this with a do while, you don't need to repeat this code, because here we are repeating code, and with a do while you can just do this, you know. Do while loops aren't that oftenly used in programming, but they do find their their uses sometimes, so keep them in mind. I told you how it works. So this thing is executed at least once, execute the statement, then checks if the condition is true, executes them again. So this is basically a repeater. Does something and then repeats it if it's necessary. Okay, so there's how a do while works. Same thing as a while, only that the statements are before the condition. Nothing too complicated. Some examples of do while. And Factorio, again the same thing which we calculated with a while ago, but this time we do while. As you see, it's a bit less code in this case. Because what do? Well, we say that Factorial is 1 for starters, and then we say multiply the Factorial by n, and then decrease n by 1. Now what's going to happen here, for example, if we enter 3 for n, what's going to happen? Well, Factorial is 3. You know, 1 multiplied by 3, but that one I don't need to write down. Then n becomes 2, then we check if 2 is larger than 0, which is obviously so we continue, and we repeat this. So n is now 2, so this is multiplied by 2, and n is decreased by 1, and n becomes 1. Then we check the condition again. Is n larger than 0? Well, obviously it is. So we go back to the execution again. Now n here then n was last one, you know, this thing is 1. So multiply by 1 here, and then say n minus minus. At this point n becomes 0. That's not a problem for a factorial because we're not multiplying after we decrease n, we're multiplying before we decrease n. So now we have n 0, and we're going to check, is 0 larger than 0? Well, obviously this thing is now false, and because this is false, this execution will terminate. This won't happen again. So this is not true, this is false, and because this is false, we continue after this thing to the console write line, and we print out the factorial. Nothing too complicated. Now, as I said in the last example, here in this example we have a system numerics and a system big integer. You already saw how to add them if you don't have them in your project. If you're using Visual Studio 2010 or 2012, you'll probably have that system numerics DLL, which I had to add as a reference. You probably have that added because your project will be .NET 4, not .NET 2.0. So you don't have to worry about adding the reference. What you do have to worry about is this, using system numerics, and then the name is big integer. So nothing too hard. If you want to use big integer, this is what you have to put as using up. Or you can do system, I won't have enough space here, system.numerics, still don't have enough space, .big integer. So that's basically what you can do if you don't want to write this thing up here. But that's using big integer for calculating factorial. Big integer is just a data type, one of those integer types. It's not a fractional type, it's an integer type, but it's much larger than it. It can remember, it can save much larger numbers. So, and all the other operations are the same, which you have come to know and love. So yeah, the reference to system numerics, you will probably have it in your project, most likely. If you don't have it, well, you just saw how to add it. Okay, factorial with do while, we'll just see it in a jiffy and we won't waste too much time with that. Okay, so factorial do while, here it is, and what we already discussed. We have a factorial which we calculate, we multiply by n, the things which we discussed. You can try this out at home, we won't play through them, I'll just show you that it works. Put in 5 by 4 by 3 by 2 is exactly 120. Now if again I put in a larger number like 100, I get an overflow exception. You can see it over here. We would learn how to deal with exceptions later on in the videos, but this is an overflow exception. Oops, wrong button. And I don't want you here. And that happens because we're using decimal. If we use, for example, long, look what happens. We compile this thing, run it, and we say 100, and it says 0. Wow, exact hit. 101 still 0. What happens here is this long number overflows, but it jumps out to the other side and becomes a number with a lot of zeros, and it actually is big enough to remember only the zeros, because each factorial basically has a certain number of zeros at its end. You have an exercise to determine exactly how much zeros does a factorial have at its end, but I'll leave that to you later on. So what we're talking about is that long or integer or ulong or those standard types, they don't throw exceptions when they overflow. When you try to save a number in them which is too big for them, and that could cause you problems. You saw that this thing said that, for example, 33, this may be this number, but it may not be this number. For example, if I write 50, you get a negative number. That should be impossible. You know, positive numbers should give positive numbers. This happens because our factorial number, we try to save in it a number which is larger than the largest number that long can hold. So it overflows and jumps to the other side of its possible values, which are negative, and then it will go on and will reach the positive values, and then the negative again, and then the positive, and at one point there will be too many zeros for it to remember, and that's why it becomes 0. Same thing will happen with int, but at at smaller intervals. Decimal reports this because decimal is a type which is commonly used when calculating money transactions, and you don't want a multi-billionaire to lose all his money because your program just can't work properly. So decimal reports for such errors through that overflow exception thing, and doesn't set the value. We'll learn how to handle those exceptions later on, but if you want to be sure that you can store everything which you want, you use the big integer and say control dot, and yeah, here we have to again add system numerics and add the DLL and so on and so on. You already saw how to do it. Actually, I can do it like this because I have it here, or maybe I can do it like this. Okay, so I'm not going to play around and add it again. You can watch 5 minutes ago I did the exact same thing, so relax about that. You can use the big integer and it will work with much larger numbers. Okay, so moving on. That's do while. I explained how it works, so I don't think there's something too complicated for that. Okay, another thing you can do with do while is calculate the product of all numbers in an interval. Now, why do while, not while? Well, because obviously if you have to calculate the product of the numbers from 5 to 6, you have to do it at least once. So yeah, and in most cases you will have to do it at least once. So we create a variable which we will name product originally, and it will hold the value 1. We read two numbers, n and m. Of course we expect them to be n to be less than m, because we will move from n to m. As you see, we have this is the controlling variable. Look, it's here in the while loop. So now I'm calling it controlling variable in my own terminology, but you probably see such, or at least similar terminology in other cases. So you have that number, you start from n, you have a decimal product in which you will accumulate the multiplication, and you say do this at least once, multiply the product by the number, meaning multiply by n in the first case. For example, let's say 5 and 8. Okay, so first time number is 5. Then number is increased, it becomes 6. Is number less than 8? Well, it obviously is. Here number is now 6, and we multiply 5 by 6. This is 6. Okay, then number plus plus makes 7 for number. Then we say, is 7 smaller than 8? Well, obviously yes. Then we go back to the do. We do it. Do what? Well, multiply by 7, because number is now 7. Okay, then number becomes 8. Then we check, is 8 less than or equal to? Less than or equal to 8? Well, it's equal to, so this condition holds. So we go back again and do multiply by 8. Here's 8. Whoops, that's the ugliest 8 I've ever drawn in my life. No, I lied, there are uglier ones. Okay, so number plus plus. Now here we get 9, and we check, is 9 less than or equal to 8? Well, this is obviously wrong, and nothing else will be executed here. This will stop, we will not go back, we will go to the next line, and this is the next line in our code, and we will print the product of the numbers. So basically that's it, nothing too complicated. Here's the demo, going to our Solution Explorer and searching for, we saw the Factorial with do while, and now we're searching, whoa, we don't have that example. No, we do have that example. Product.C#. Our examples are just a bit messed up. Okay, so that's our product, and we have some checks over here. For example, we have a check if n is less than m. As we said in the previous lecture, you can have anything in an if statement, including loops, and this is a loop. So if m is less than m, which is some sort of error handling, well, okay, do the magic which we already discussed how we do it, and in the opposite case, just write that n should be smaller than m. That's sort of error handling. Okay, and the other part you already know. You input two numbers. You start with a product which is 1, then you have a number num which is equal to n, and then you multiply product by n, and then you increase that n thing, the thing that remembers n. You increase it with 1, then check, then multiply again, then increase, then check, then multiply, then increase, then check, and so on. And at the time when this check is no longer valid, we print out the product. Start this thing, and we'll get 4 and 7 I said, and this will give us 840. That seems like too much, but 4 multiplied by 5 is 20, multiplied by 6 is 120, and multiplied by 7, yeah, that seems logical now, for 840. So this thing works correctly, and it works fine. Now what will happen if I write down 4 and 4? N should be smaller than m. So we're expecting a range which is of two numbers, of which one is larger. Okay, so if I write it down the other way, for example 5 and 4, well, I got an exception because I input two numbers on the same line, and at this point in time we don't know how to do it in C#. We'll learn it sometime after that. And again, the error n should be smaller than m. Okay, so I'm not going to discuss this too much. Now, if I remove this conditional statement and leave it like this, the code will still work. Look, I'm removing this conditional statement which does my error handling. Okay, compiling it and formatting a bit. I'm doing the formatting with Control E plus D, basically holding down Control and then ED. Yeah, hope you got what I mean. So if I do it like this, this will still work because num is equal to n. So give me the product of the range from 4 to 4, which means give me the product of 4 basically by itself, without any numbers. So if I do now, for example, 10 and 10, this will give me 10. Why does it give me 10? Because I have a product which is 1. This executes at least once, at which point we have product multiplied by number, which number is actually n, which is 10, which I had 10, and this is 1, so 1 multiplied by 10 gives 10, and increasing the number, this loop stops working and we print out the product. So this is also an acceptable solution. Okay, continuing on, we saw the product of an interval. Now we're going to see for loops. Now for loops are probably the easiest thing to use for repetitive code if we know how much times that code repeats. Now what I mean is, for loops consist of 3 parts. Basically, for loops are used to say start from 0, continue to, for example, 5, and then increase by 1 every time. So this means that this loop will execute exactly 5 times. We'll see what I mean in a moment. So for loops consist of an initialization, a test, and an update statement, and of course the loop body. How it works we'll discuss now. So the initialization is used to initialize variables. Basically, you can initialize any. You saw the counter variables and the so-called by me control variables, which we used a lot of times in the previous examples of while and do while loops. Well, this for loop has the ability to define its own control variables and to keep them within itself. Now, this gives our code much more compactability, so we don't have to have some flying variables out of the for loop. We have them in the for loop, and they live with the for loop, and this variable will be visible only to the to this part of the for loop, not to the outside code, not here, not here, only here. Okay, and here also. Okay, so this is the initialization. You can initialize one or more variables, and it's usually used to declare some sort of counter variable. Okay, the test expression. Now the test expression is the loop condition, or the check, or the condition, or whatever you like to call it. It's the same thing, absolutely no difference than the loop condition for a while loop or for a do while loop. So that means that it's a Boolean expression. It returns a true or false result, and while this thing is true, the loop executes. If it stops being true, well, the loop stops executing its code. Okay, so this is the loop condition thing. Now it's most commonly used to compare the counter variable to some other variable or constant. So basically the most often form in which you see a for loop is having a counter variable, a comparison of that counter variable to some constant or non-constant number, and then the update expression. Now the update expression again will most probably be used to update one single variable, and that will be that counter variable. And the update expression can be anything. Of course we have here plus plus, but we can have multiplied by 2. We can have even more than one expression. We can have, for example, number plus plus, comma, and j plus plus, for example, if we have a variable j somewhere. Now the only peculiarity here is that you don't separate with semicolon, you separate with only comma. But that's not important. In most cases you will need only one statement here. You can only have one statement in the test expression. This is always only once, and only one variable here. That's the general case. And this variable, this counter or control or whatever you call it variable, will most probably be used in all places of the loop. That's what a for loop is built for. Not that you could create a variable here which you never use in your lifetime, or use somewhere else in other situations, but that's not a common usage of the for loop. You can increase another number, not the counter variable, but again, that's not the purpose of the for loop. So generally this is what the for loop is made for, not for something else. For other situations you can quite simply use a while or a do while loop or whatever you wish. Okay, so one peculiar thing about the update expression, it doesn't happen here. It's written here because it's part of the loop, but its actual execution is way down over here at the end of the loop, before the closing bracket. Imagine that you have statements. After all of the statements, then you have the number plus plus thing. So this is at the end. If you want to remove it from here, you have to move it at the end of the loop, as if it's over here, for example. Number plus plus. Okay, so this number which you initialized at this spot, you can use it inside, you cannot use it outside, and you cannot use it here either. So yeah, basically everything which needed to be said was said. The most important thing, remember that this is written here but is executed here at the end of the statements of the loop. That is, before the last bracket we do number plus plus and then go back and check the condition, and then do the statements and then do number plus plus, and then go back and check the condition, and then execute the statements and do plus plus, and then go back and check the condition until the condition no longer holds, at which point, when the condition stops holding, when this thing becomes false, this loop finishes its work and code continues from down here after the loop body. So that's basically it. And again, as each and every other loop, you can have a body of one operation which is not in brackets, but always use brackets. So it is possible to only put one operation here and avoid the brackets, but it's not good code. Better put the brackets even if it's only one operation. So, examples for a for loop. Most common use of for loops is either traversing arrays, we'll talk about that a little bit later on, counting through numbers, or executing something a fixed amount of times. So, here's an example of counting the numbers from 0 to 10, what we had with a while loop. We start with number equals 0, number less than 10, number plus plus. That means that the first time which we get into this code, number will be, guess what? Those of you who guessed 1 didn't listen that this number plus plus comes over here at the end of the expressions in the loop body. So those of you who were right, remember that number plus plus executes at the last moment. So here we will have first time number is 0, then plus plus, 1 is less than 10, print 1, plus plus again, 2 is less than 10, print 2, and so on and so on and so on until we reach, guess what? Well, we reach 9. Is 9 less than 10? Well, obviously it is. We print 9, sorry about that, and then we say plus plus, at which point 9 becomes 10. Is 10 less than 10? No. So we exit the loop and we do not print the last number 10. So 10 is not printed when here we have less than. If we had less than or equal to, then we would print 10 also. Here's the for loop to calculate the factorial. Factorial begins with 1. We start a number which is 1, continue to n, that is, we multiply from 1 to n. Actually, we could have started from 2 with the same result. So from 1 to n or from 2 to n, inclusively, see this less than or equal to, and then increase I. So first time we have factorial multiplied by 1, then we have by 2, then we have by 3, and so on and so on. And then we have by n minus 1, and then we check, we increase n by 1, and this thing becomes n less than or equal to n, which is true because we have equal to. Then multiplied by n, and then this loop stops working and exits. Those are examples for what you can use a for loop. Now there's some more complex for loops which you can use. Here's one of them. Initialization of several variables, both of them integers in this case, I1 and sum1. Obviously here we'll be summing the numbers, the powers of 2, because look, I goes to 128. That's the what is it, 6th power, 7th power of, exactly 7th power of 2. 7th, yeah, I think you know what I mean. 7th power of 2. So here we have then I multiplied by 2 and sum with added I. So the first time sum and I will be, guess what, 1, because they are initialized with 1. The first time they are what they are initialized with. Each and every next time I will become twice larger, because there is I multiplied by 2, this is by 2, and then sum is added I. sum is added I, and I is multiplied by 2. And this comes at the end. And that's basically it. And here we have some printing of those numbers. First time they are 1 and 1, then they're 2 and 3, and so on and so on. You can calculate them by yourselves. Okay, so some demos of for loops, the things we just saw in the examples. We have powers, we have continuous, we have a lot of things. Here are the for loops. And we increase this thing in size. Here's the printing of the numbers from 1 to 10, 2 empty lines to divide it from the other stuff, a factorial, which is from 1 to n again, where n is 5, and this thing with the powers of 2. We start them, here you can see all of them. First one is the numbers from 0 to 10, exclusively. Here is the factorial of 5, and here is the i's with the sums of the powers of 2. Here are the powers of 2, and the sums of the corresponding powers. Up until the corresponding power, that is. So, this is just... I don't think you will be using this kind of for loop anytime soon, because it's more complicated than it does work. I mean, it's something you can use, but it's more like showing off than actually doing proper work. If you can write some code simply, just write it simply. Don't be a bad guy about it. Don't try to show how many knowledge you have of what kind of sophisticated for loop you can write. No, that's not necessary. Just write it simply. How can you write this simply? Well, several ways. For example, I decide that my control variable is going to be I. I don't need the sum right now. Now, I starts from 1 and continues to 128. This obviously is a for loop which will traverse all the powers of 2. Great. Now I will create an integer variable which is sum, which is initially equal to 0, because that's logical. Now I will print at each turn, actually not to 0 but to 1, because I is 1 at the beginning. Okay, so no, not like this. To 0. Sum is always 0. If you're doing a multiplication, it's always 1, but if you're doing a sum, it's always 0. I'll show you what's 0 in a moment. So we do want to print sum and I at each turn, so we're going to print them. And now what do I still need? Well, I obviously need to calculate my sum up until this moment. And what is sum? Well, it's something fairly simple. It's sum equals sum plus I, which is the same as sum equals plus equals I. That's the same code. If you start this again, you'll see the same results. 1, 2, 4, 18, so 16 and so on, with the sum getting up to 255. If you don't believe me, scroll back the video 1 minute and you'll see the results are the same. So this is much better code than the one we had before. Why are we showing you this since we're saying it's not very good code and not very understandable? Because in some cases you will meet code which looks like this, which not like this, but like the one which we fixed just now, and you will need to understand it. So we're telling you what exists out there, and we're making sure you are aware of what exists, and making sure that you don't decide, wow, that's so cool, and I will always use this sort of weird typing stuff to make my code. No, don't be a nerd about it. Just write something that's readable. That's much better than showing off. So we're showing you just so you know that these things exist and are possible, but not recommending that you use them. Now, using a for loop to raise something to a power, doing for loops is very, very effective when you want to do something a certain amount of times. For example, how do you raise a number to a power? Well, you need to multiply that number by itself a certain number of times. How do you do it? Read the two numbers, get a result variable which is 1, and then start multiplying into that result variable from 0 to m. That is, repeat this piece of code m times, because we start from 0 and continue to m minus 1 actually, because we have less than m, and that's exactly m times. And then just print out the result. And this will work for 0 too, because if we have n, which is some number, for example 5, and we have m, which is 0, then we'll have result equals 1, I becomes 1 and it's less than 0, I becomes 0 and it's less than 0, which isn't true, because 0 isn't less than 0. This will not execute and will go down, and we'll have n to the power of m is, what is the result? Well, result is initialized with 1 at the beginning. So that's a true answer mathematically speaking. Any number to the power of 0 is 1. So this code will work properly. And if m isn't 0, well, obviously if m is 1, this code will execute exactly one time, and we will have result multiplied by n, that is 1 multiplied by n, which is exactly n. If we have twice, well, if you have m equal to 2, well, obviously we will have result multiplied by n multiplied by n, and so on and so on. Now, this approach works faster than using the standard math library and doing math.pow and m. Now, why is it faster? Because math.pow works for double numbers, for floats, for very weird variations of powers. So it uses more universal methods, and these more universal methods involve a lot more calculations. So it works slower than just doing a for loop. So anytime you can do a for loop instead of doing a power, doing a math.pow, well, prefer the for loop. Okay, calculating n at the power of m. We'll go to our live demo. We have this power over here. And okay, what do we have here? Well, we have the number n input from the console, the number m input from the console, and the code which we just discussed. Again, not going to discuss it now because we already said what it is. 4 to the power of 2 is 16, and 4 to the power of 0 is exactly 1. Of course, if we input a negative power, it won't work, and in that case we will need to use math.pow or make some alterations to the code which will actually work with negative powers. And how do we do something which works with negative powers? Well, basically make an if statement, if like this, and say if m is less than 0, which means negative power. Well, if m is less than 0, then do the same code. Actually, if m is larger than or equal to 0, this code works. Else, in the opposite case, we can say that for I from 0 again to m, but not less than, and not, yeah, actually this works, from 0 to minus m, because we want m as a positive number. What do we do actually when we need to raise a number to a negative power? Well, we actually make the corresponding deletion, the corresponding divisions instead of multiplications. So basically, negative power means positive power means multiplication, negative power means division. So what we have to do here is, as much times as we have m, for example, if we have m to the first power, then we need to have result divided by n. And because result is a decimal variable, this thing will work, and this thing will give us a non-integer result. So, for example, if we input n as 4 and m as minus 2, this should be the power at which, this should be 4 at the power of minus 2. You can try and do the reverse multiplication and see if it works, but I think that this should be the right code. So this is how you can make this code work for negative powers. Basically, negative power means n at the power of -1. I'm going to do it as a comment. N to the power of -1 means 1 divided by n. And n to the power of -2 means 1 divided by n to the power of 2. And so on and so on. You can get the other results from this sequence. At least I think that that's the truth. I could be wrong. I'm not absolutely sure, but I think that this is the meaning of negative powers. I haven't done such math in a while, so you excuse me if I'm wrong. But if this is the sequence, this is the code to generate it. Okay, so that's the demo, and continuing on with the continue operator. How proper. And we're still getting some messages. Not answering them now, however. So, sorry. So, continue operator, we already saw the break operator, which functions like breaking the loop and leaving it. Well, the continue operator does something similar in the way that no code after it from the loop will be executed, but not entirely, but for the current iteration. So, continue does the following thing. It says, okay, I've reached some case which I do not need to consider, which means that I can go to the check condition and not continue doing this stuff. So don't do this stuff, don't do anything after me, but go back to the loop condition over here, no matter if it's a while or for loop, just go to the loop condition and continue on from there. That means check the condition and go on and execute this code again. So continue operator is the opposite of the break operator. The break operator, if we have a break operator, not a continue one, if we have a break operator, this will not execute anything after it. After this semicolon, nothing will be executed, and this will jump directly to the line after the for loop. The continue operator will not jump here. It will not jump here. It will jump back. It will jump to the condition and check this condition and continue with the normal execution of the loop. Now, one major thing that happens when we use a continue operator in a for loop is that it actually executes this. So in my drawing, it would be more appropriate to do this. So basically this is what happens. It executes the incrementation or the update operation and then checks the condition. So basically, if you imagine that this operation is not here but is over here, then the continue operator goes through this operation and then goes back to the loop condition. Imagine it however you want. The idea is that the continue operator executes this. That is, it executes nothing here, only this, which we know that is generally executed at the end of the for loop, and then checks the condition. Okay, so what does this thing do? Sum of all odd numbers from 1 to n, which are not divisors of 7. This is wrong. This is a wrong. This is wrong task description. What they mean to say here is which are not divisible, dividable. Not sure about my English here. Not divisible by 7. That is the divisor of some all numbers, all odd numbers. That means go +2, not just plus, a +2, which are not divisible by 7, which means which have a remainder of 0. That is don't include, sorry about that, don't include numbers which divided by 7 have a remainder which is equal to 0. So basically what we do here is go from 1 to n inclusively, because that's our task description. This is an inclusive range, and we add 2 to I every time, because 1 plus 2 is 3, 3 plus 2 is 5, and so on. So that's how we will visit all odd numbers in that range. And if we accidentally meet a number which is divisible by 7, we just say continue. That is, don't include it in the sum. As we said, this line will not execute when this line executes. And this will get us back. We'll do the I plus equals 2, which will mean that we will get to the next odd number, and then we'll check the condition, and then we'll go through this loop body. And if this thing is again divisible, we'll do continue again. But if it is not divisible, we'll add I to the sum. And that's generally what our current continue operator does. And here's a live demo of that continue operator. Some odds, and here I think we'll have printing of the numbers. No, we don't have the printing of the numbers. That's why we'll make it. Now this is bad code, as I've already said, and we should fix it. Okay, so we will write I, and before the continue operator we will write the string divisible by 7, so skipping. You can, maybe the more appropriate word for continue should be skip. You know, if this is executed, skip the rest of this iteration. You know, but yeah, whatever. I don't know what their decision making was when they used continue. Probably they have some good reason for that. Okay, so basically this means we're skipping. Continue means skip everything here, cancel that order and continue with the next one. Okay, so starting in now you see all numbers which we pass through. For example, if I say 27, we will get 1, 3, 5, 7, and 7 is divisible by 7. Maybe I shouldn't have made a right line. Okay, so right here and a right line at the end. This will make my numbers appear more friendly, more user friendly. So here's what we have. Starting with 1, we go to 3, 5, we reach to 7. What happens when we reach to 7? Well, we say, well, okay, this 7 is divisible by 7 and gives a remainder of 0. So in this case, we will print that this is divisible by 7, and we'll say continue. And this sum will not be executed. This thing will not be executed. Any code that is from here on, and here, and here, and here, and here, will not be executed. That is, if I wasn't using right line over here, this right line would not be executed, and we will have 9 over here. So I'll show it to you now. If I write here right, not right line, right, not read, right, start this, 27, here my, whoops, wasn't what I meant to do, Control F5, 27, and zoom in. Here, skipping, and we have 9 on the same line, because we don't have a right line anywhere, because this continue cut everything down. Okay, so for example, if I was to write here console right line, this would never execute, and compile, I'd probably get a warning even. No, I didn't get a warning. Yeah, I get a warning. Unreachable code detected. This code will never execute because we have a continue exactly before it in the same body of an if. Now this is possible to execute because if this if doesn't execute, this won't execute, so continue won't execute, so we'll exit the if and do this. But if we have a continue and after it exactly something, well, it will never execute. So yeah, we start this and you'll see that this thing never executes. Again, for 27, for example. And here this thing works. You can calculate the sum and you'll see that the sum of all these numbers, up to 27 inclusively, is 168. Okay. So continuing on forward, that's the continue operator, not too much. For each loop. The for each loop is something pretty interesting, and it works on collections in C#. Now collections are generally arrays, lists, hash tables, sets, basically any type of data structure which holds more than one element at a time. Now the data types which we've studied so far are data types which hold exactly one variable at a time. The only exception is the string. You know that the string is actually a bunch of symbols, a bunch of char symbols, and you can access each one of them. Well, with the for each loop you can traverse or go through or track through or whatever you like to call it all elements in a string. You know, you can print out each and every one of the symbols in a string. You can do the same thing with the for loop, but the for each loop is much more convenient. So what does a for each loop look like? Well, you say for each, and then you have something like a condition, but not really. You say type, a type of variable which you want to use, the name of that variable which you will use, and the collection in which you want, and the keyword in. Now what this thing does is it goes through every element in that collection. So for example, in a string, for example the string ABC, if you say for each character, because strings consist of characters, for each character in ABC, for each character, for example CH, that's the name of the character, what will happen? Well, this thing will execute exactly 3 times, because there are exactly 3 characters here. 3. Okay, and each time element, that is CH in our case, will have a value of one of the characters in that string. For example, the first time it will have A, the second time it will have B, and the third time it will have C. And at each iteration you can use that variable and, for example, print out its value or do something else. Okay, so yeah, as I told you, this iterates through all elements of a collection. Now collections are a lot of other things, because you've only studied strings so far. I gave you an example of strings, but if anybody knows arrays or lists or hash tables or whatever, well, those things can also be traversed by a for each loop, and it will go through all of the elements in that thing. Okay, example of for each loop. Now this thing over here is an array of strings, not just a string, an array of strings. So now it would be easy to imagine that the string is just like the integer data type. So this is how you define an array, nothing too complicated, but this thing looks like an array, and it has different strings, which are the days of the week. And when we say for each string day in days, this will pass through each and every element of those strings. Now we'll discuss arrays later on, and we'll discuss for each in arrays later on also, so you shouldn't be too much worried if you don't understand everything which is here. But I already gave you an example of traversing a single string. Well, this is an array of strings which you can also traverse. Okay, so basically what will happen here is we will first print Monday, then we will print Tuesday, then we will print Wednesday, and so on until we reach Sunday. Now the good thing in for each is that you don't have to worry about any indexes, any array lengths or anything. It just gives you each and every element. You don't care about how it gives it to you. It handles that stuff. So in this day thing, we can get each and every variable from this array of variables. Like for example in a single string, which would be, for example, string alphabet equals A, B, C, D, and so on. You know the alphabet, I'm not going to write it. And we say for each char C in alphabet, because the string is also a collection, we can say, for example, console.writeLine this is the letter, for example, C, and this will get each and every letter of this alphabet and place it on the console with the console.writeLine. So we will basically get, this is the letter A, this is the letter B. This is the letter C, and so on and so on and so on. You can also, for example, pass through all of the alphabet and get the ASCII codes of the numbers of the letters, and for example calculate their sum or whatever you wish to do. So that's what a for each loop does. We have an example over here, for each loop, and here's how it works. We have a string array of some days, and we have Monday, Tuesday, Wednesday, Thursday, Friday, and so on. And I need to learn how to turn off my toast notifications. Actually, I know how to do it, but I'm too lazy to do it. So we have these things, and we'll get them printed each on a separate line, like this. Monday, Tuesday, Wednesday, and so on. That's what a for each loop does. For example, if we had an array of numbers, int array, this means array, numbers equals new int array, and the numbers in this int array are 1, 2, 7, 15, 20, for example. And if we want to calculate the sum of all numbers in the numbers array, we can do this thing. Numbers, for each number in numbers, we will create a sum variable, which as we said, has a value of what? Of 0. We create a sum of 0. There should be a semicolon over here. So sum plus equals the number which we have reached at the current moment. We can also print out now summing and the number, which is num, or you can write it like this if you like to. This is a formatting string. We've already spoken about reading and writing to the console, so you should understand what this means. So we add number to the sum, and we say console write line at the end, the sum is, and we put our last number. My typing at the keyboard is probably driving you crazy, but don't have a good microphone, so can't help it, get used to it, sorry about that. Starting this thing, and it says now summing 1, 2, 7, 15, 20, and the end result is 45. Is it true? Well, we have 1, 2, and 7, which is 10, then we have 15, 10 plus 15 is 25, and 20 more gets 45. Well, seems like it's working properly. So that's a for each loop and an example with it. Continuing on, moving on with nested loops. Now, my advice is that you take a break right now. I'll continue with the video, but if you need to rest a little bit, now's the time. You can pause the video, go for a snack, go for a beer, go for whatever you want. I just went for a glass of cola, and continuing on with nested loops. So, nested loops are basically loops inside loops, or this is the Russian matryoshka doll, if you know it. So, having a loop inside another loop is just like having a conditional statement inside a conditional statement, which you've already done in the past lecture in the exercise. So, what are nested loops? Well, loops inside loops. As I said, you can have anything in a loop, including another loop. Now, the most often example would probably be 2 for loops, one in each other. They are pretty oftenly used. There are other cases as well. Now we'll see some examples for them. For example, say that you want to print a triangle which looks the following way. On the first line you have the number 1, then you have the numbers 1 and 2, then you have the numbers 1, 2 and 3, and so on and so on, 1, 2, 3, 4, 5, 6, 7, and so on, until you have 1, 2, 3, 4, 5, la-di-da-di-da-di-da-di-da, to n. And these are exactly n lines. You already imagine how many, what the triangle looks like. So how do you do such a thing? Well, obviously we have to start dividing the thing into several subtasks. Okay, so how do we print a line of numbers? Well, obviously with a for loop. We can use a for loop which begins from 1 and continues to 2 or to 3 or to 8 to print a line of numbers. So this just looks like for int, for example, number, which begins from 1, number is less than or equal to 8, and number on the other line, because I don't have any space, number plus plus. And in this we just say console.write of number plus 1 space, so we don't get them gluing together. So this is the equivalent of this. So we have printing of a single line. How can we print multiple lines? Well, pretty much the same thing. Since we have the code for one line and we need to repeat the execution of that code for each and every line, what we need to do is put this code in another loop. And that other loop will be a for loop, which begins from row, for example 1, continues to row n inclusively, less than or equal to n, and says row plus plus. That is, passes through each and every row from the first to the last. Now, this thing will probably work fine. We put an additional bracket over here. So for each and every line, we print the line. Now, what does this number have to be? It couldn't be 8 because each of our lines would be 8 numbers. What should it be? Well, with simple inspection we can see that this is the first line, this is the second line, this is the third line, and so on. And this has 1 symbol, 2 symbols, 3 symbols, 3 numbers, that is. So basically the number of the line corresponds to the number of numbers on that line. So this thing here should be n, not 8. So we write down n. Sorry, not n. Speaking wrong things here. This should be row, because row is the representation of the current row which we have reached, and n is the number of total rows. So this here is row, column, semicolon, that is. And one thing more that we have lacking, and probably some of you have already noticed that, well, we need to have a new line at the end of each row. So how do we do that? Well, this is the end of the printing of each row. So here, after this nested loop, we have to have a console.write line. And that's pretty much it. And here's the code which does it. Pretty much the same thing. We read a number n from the console, and we say from 1 to that number, go through all the rows, and for each row, for each of the columns in the row, okay, another name, go to the number of the row, because at each row we have the same number of columns. At the third row we have 3 columns. At the second row we have 2 columns, and so on. And then we do a write line at the end. At each row. This is a new line, this is a new line, and so on and so on. Here's a demo of that particular triangle printed out with 4 loops, nested 4 loops. So this loop executes, this loop starts executing. It goes to this. This loop executes fully, then a write line is executed, then this loop checks its condition and goes into its body again. This internal loop again executes fully, and then a write line is done, and so on and so on. It's probably easier to visualize than to explain with words. So here's the example of a triangle, 4 lines. There are 4 lines exactly. Okay, so this was the example of our triangle, and now we can continue further on. How to get the primes in a range? We already have code which checks if a number is prime. This code over from here to here checks if a number is prime. We already wrote that while we were researching while loops and do while loops. So this code is the same, or almost the same code which we saw at the beginning of the lecture, at the beginning of the video. So we don't need to explain that again, and since we have it, we can use it. And how can we calculate all the primes in a certain range? Well, since we have the code which finds a certain prime, or rather determines if a certain number is prime, well, all that we have to do is pass through the range with a for loop and pass each number in that range to our code which determines if that number is prime. So that's basically what we have here. We have the code which determines if a number is prime. It uses the variable number. The variable number is the control variable of the outer loop, and it just passes through all elements in the range, starting from n and continuing to m. That's how we pass through a range with the for loop. And we just pass that number onto our code which checks. We have a boolean variable prime, which is again set to true as in the previous example with the while loop. And at the end, if we determine that the number is prime, and that is, if this thing has stayed true throughout the course of this iteration, if this has stayed true, then we will have the number printed out. If this has become false at some time in the iteration, well, we won't print it out. And simple as that. So printing out all numbers in an interval from n to m, whoops, didn't mean to do that exactly. All numbers in an interval from n to m can be done in exactly this way. So here's the main method. Here are our main heroes, the for loop, the while loop. Here we have some other checks, for example, if n is larger than 1 and so on. Basically this is error handling, because we don't want to see the prime numbers beginning in the interval from 1, because 1 is obviously a prime number and it will mess up our calculations. And we also want m to be larger than n. That is, we want to have an interval of the type 5, 7, not, for example, 7 and 5. That the second thing is wrong, because it won't work. So this is what we're checking over here, and basically that's our entire task. Now I'm not going to discuss it too much, because this entire code we've already discussed in this video. The only addition to this code is this num thing, which comes from traversing each and every element in the range from n inclusively to m inclusively and passing it on as a variable over here. And then another addition, which is if the number is prime, then print it out. In every other occasion, don't print anything. And that's basically what we're doing here. So starting the program and doing a range from, for example, from 5 to 10, and we get the numbers 5 and 7. Now 5 is a prime number, 7 also is a prime number. If we do this for 20 and 100, we'll get, if we do this like that, we'll get an error. But if we do it properly, 20, enter, 100, enter, then we'll get all prime numbers in that range. Again, how does that happen? Well, we just pass through each and every number of the range and print it out only if it is proven to be prime. That is, print it out only if it is not proven to be not prime. Basically said the same thing over and over again, but said it in different ways. So if somebody has forgotten how to write this, well, feel free to check back in the video and see it again. Okay, continuing forward. Now, this is a good advice from now on. Use code that you've written before. Find ways to use code that you've written before in such situations. At one point in time, we will learn how to use methods and how to do things like that. Get this thing in a method, and this method will check if a number is prime. Check prime, or more likely is prime, of some number, and we'll do this. If the number is prime, then print it. And isPrime is actually a method which contains this code, and we're actually reusing it with just one word. isPrime, its name. So that's what we're doing with our loop here, and nothing more complicated, nothing too much to worry about. So that's our code, and we continue on. We saw the primes in range demo, and now we'll see some info about jump statements. Now we saw nested loops. You can continue on nesting. Of course, you can nest a while loop in a for loop, but you can also nest a for loop in a while loop, and so on, each and every way you can think of. Now, jump statements. Jump statements, you already saw break and continue. Now we'll see additionally go to. What does go to do? Well, several things. First, how does continue work? Now, in while and do while loops, this thing jumps to the test expression directly. I've already drawn it to you, but do while and do while loops only have a test expression, so there's nothing else to jump to. Now, sorry about that. For loops have an update expression. So for for loops, continue goes to the update expression and skips all other code before that. So from the continue to the update expression, nothing happens from the code in the for loop, and then we go on to the test expression. I already sketched that a few times, so I guess you've already figured it out. Break always exits the innermost loop. Continue also works on the innermost loop. That is, if you have nested loops, continue and break will work on the loop which they are directly in. That means the first loop in which they are in, the smallest loop which they are in, if you can imagine it that way. Okay. Now, go to is a specific part of programming which was used in the past because there were no loops and stuff like that. Now what go to does is it goes to a label. Labels look basically the same way as they look in switch case statements, and that's some string of words followed by a column. That is, for example, this is a label. This is a label, as it says, and you can say go to this is a label, and this will mean at this point of the execution of the code will switch back and jump to this part, to this is a label thing. So yeah, that's what go to does. Now, it sounds like something cool, you know. You get to some point and you wish to jump to another piece of code. Now, there are many reasons why go to is not a good idea to be used. Now, some things come from strictly conceptual and theoretical parts of computer programming, in the case that generally we have mathematical ways to determine how computer programs are going to work. So we can build state machines which can depict the work of machines and make them easier to understand. So we can depict loops through mathematical models. We can depict if-else statements. We can depict even methods, but we can't depict go-tos, because if we have go-tos, now this thing is strictly like a tree. I mean, you start from the beginning, from the root, from something low, and you can go up, which is fairly logical. You know, you eventually will go up. Now with go-to statements, the green thing is the go-to. With go-to statements, you can do this and this. Go in the middle of a go-to, and then from here go this, or go here, or go here, or go here, or go everywhere you wish, absolutely each and every place. Which at the beginning sounds cool. Yeah, I can go everywhere, I can go here, I can go from the else statement to the if statement, I can go to the input data, I can go anywhere. Yeah, it sounds cool, but look what happened to the drawing. It's a mess. You cannot understand what happens. You cannot create a model of your program which shows how it works, because it gets too complicated. And that's why that's one of the reasons go-to is considered harmful. It's very easy to slip up and to make your program too freaking complicated. So basically don't use it. If you're really keen on reading material, you can check this go to statement considered harmful, Dijkstra. Now Dijkstra, I'm not sure how to read that name, is a great computer scientist who's thought up a bunch of algorithms which do a bunch of cool stuff. This guy, along with a lot of other guys, has said go to statement considered harmful. He's written an entire article about the thing. He explains all those things. So if you're keen on reading, read that. If you're keen on listening to the experience of other people, listen to our experience. Don't use the go to statement. Now we're showing you that it exists so that you know that it isn't something cool. We're showing you that it exists, and from now on, don't use it. Just forget about it. Don't. Find other ways to program without. There's always a way to write your code which will allow you to make code which works properly, correctly, and understandably. And don't go to the dark side and use goto. Goto is the dark side. It's easy, but it will mess you up. You will become like Darth Vader. You will breathe through. No, you won't become like Darth Vader, or at least not from goto. But it's not a good idea. Just take it as given. Okay, so here's an example of gotos and continuous and breaks, and I'm giving up on explaining what happens. So basically, that's what happens. 2 for loops. Now, continuous and breaks will break the innermost loop. This continue affects this for loop. This break affects this for loop, not the outer one. This goto doesn't affect anything, but it jumps wherever it wants. Breakout can be here, it can be here, it can be anywhere else, and you can jump to wherever you want. So this thing is a label, and you can create your labels. You just write this and then say go to this, and it jumps. How it jumps, why does it do it, you don't care. Don't use go to. Please don't. Stay on the bright side of the force, of the programming, of the whatever. Just don't use go to. So here what we have here, well, each time that inner is divisible by 3, we will do a continue. That is, we will skip the number 3 for inner. So this thing will go to the update, and then we'll go to the condition. That's what happens. Okay, break. Each time outer becomes 7, that is, when this is 7, this loop will not execute. Basically, that's what happens. That's, in this case, it's the same as putting a continue here when outer is equal to 0. It's the same thing in execution, not in theory. And here's the goto, which functions in a completely weird way. I'm not trying to explain it to you. I already explained several times what continue does for loops and for while loops. Break, we already saw it. It's pretty simple. You most often use break, not that often continue. Now, some people ask me, is it better to use continue or break instead of thinking up a good condition for the loop you're using? Well, generally, if you can think good, understandable, and short, or at least relatively short condition for your for loop, understandable condition for your for loop, and you can write it in a reasonable amount of time, then do it. Then make a good condition. If you can do it in a reasonable amount of time, in a reasonable length, and reasonably understandable. If it's something if not using break will make your life 10 times harder, and you have to write a super complicated condition, then don't use the condition, but use break. Same thing goes for continue. You know, the soul of everything is simplicity and understandability. Generally, conditions are easier to understand than searching for some weird case down in the code of the loop. But when the condition becomes too weird itself, that doesn't help, and that ruins the whole thing of the loop. So you gotta learn to choose the lesser evil. I mean, make a good condition as possible, and if there are side effects, well, isolate those side effects in breaks. Generally, strive for understandable conditions. Now, understandable conditions means short, but not too short, like while true, and relatively long, but not too long as 5 lines of expressions, or even 2 lines of expressions separated by ORs and XORs and ANDs and stuff like that. So be careful about that. Use your head. That's the most important thing. Use your head. Okay, more examples with loops. Here we have 4 nested loops. Now, once you've started doing something like this, you're probably on the wrong track, or your program isn't, you're not writing a good program. Now, at least once we've learned how to use methods, from that point onward, you shouldn't fall in situations in which you have to do 4 nested loops. It shouldn't happen. Okay, so here we have something called magic numbers, for which we say that magic numbers are numbers in the form ABCD, where each digit is a letter. So that means 4 digit numbers, for which A plus B equals C plus D. How do we generate these numbers? Well, for each first number, and for each second number, and for each third number, and for each fourth number, we do a loop from 1 to 9, 0 to 9, and so on, which passes through all possible digits for each position. So basically we'll start for this position, and for each of these positions we calculate each of these positions, and for each of these positions we'll calculate each of these positions. So basically the last digit will move the fastest. If you start printing these out, this will change the fastest, this will change a bit slower, this even slower, and this the slowest. You can imagine what happens. Now, it's good to have brackets over here, but again, we don't have too much space on the slide, so we've done it like this. Okay, and how do you determine which are these numbers? Well, you just say, if A plus B equals C plus D, then write the number. Else, don't write anything. Now, there's a smarter way to do this, and it comes from the fact that this long equation is pointless. That is, if we have, and this loop is pointless also. So, can you write it with 3 loops? Now, I gave you some hints. Now, anyone who wants to try it for themselves, pause the video now, because I'm going to give spoilers. So, spoilers alert, 3, 2, 1. How do you solve this with 3 loops only? The 4th loop is unneeded. It's it's an unneeded extra. Why? Well, because from this equation you can easily go to D is actually equal to A plus B minus C. That's simple math. You move C over here and it goes with a minus sign, and yeah, you get it. And also D should be larger than or equal to 0, and D should be lesser than or equal to 9. So this loop is unneeded. You can just go with the 3 loops A, B, and C and say, if that is int D equals A plus B minus C, and then check if D is more than 0, and at the same time D is smaller than 10, then this is a number and you do the right line. Console right line, so on. I think you got the idea. So when this is, if we get such a D and this D is a digit, because why is D larger than 0 and less than 9? Well, because this has to be a digit, not a number, And if you have, for example, d equal to 12, which will happen in this case, you shouldn't have a number with 5 digits. You should have a number exactly with 4 digits. So that's what we're checking over here. Nothing more complicated than that. So that's the hint how to solve the task. Solving it I leave to you. And a live demo of those happy numbers. Go to the Solution Explorer. Here's the happy numbers. Now this is better formatting. This loop ends here. This loop starts and ends here. This loop starts and ends here, and so on and so on. And here's the dump check with a plus b equals c plus d. Start this thing here, all the happy numbers. Now you'll notice that not all of them will be printed out because the console has a limited buffer. That is, it remembers a certain amount of lines from the start of its printing. So it can't remember the very first. For example, it can't remember 1111 because there's just a lot of numbers. If you want to print them out all, you have to redirect the console. How do you do that? Well, you open the project, you open it in File Explorer, you go to the bin. Here's where your executable file lies. Of course, if you compile here to release, if you set this to release, in here you will have in the bin folder, you have another release folder in which you have another exec, but we're not too worried about that. Now what you can do in Windows 8, you can say open command prompt as administrator or not, or just hold down shift, right click, open commando here. Did I say commando? I meant command window. Command window, not commando. And you say happy numbers, write the name of your executable, and then this thing. It looks like the symbol larger than, it just means arrow or whatever, to, for example, some random file which you can think of. For example, output file.txt. No requirements for the name. Press enter, and you saw the appearance of this output file.txt. And here you see all the numbers. Now here we've saved them to a file in the file system without using any type of more sophisticated coding. So we didn't use file system access and APIs in Windows. We just wrote to the console and redirected the console the way I showed you. Okay, so hope you understood that one. How can you print all of the combinations in lottery 6 out of 49? Now, what is this? This is a typical lottery combination in Bulgarian lottery. So 6 out of 49, you can mark up to six numbers out of a total of 49 numbers. Of course, these 6 numbers can be must be different. So how to print them all? Well, start from 1, continue to 44 for the first loop, for the first number, because they have to be different. You can't go to 49 because they have to be different, and you have to have a total of 6 numbers, and if this is the first and each one is to a larger number, then here's where you should start. So basically that's it. And you just nest loops and loops and loops and loops and loops. This could give you an idea how you can generate all of the combinations of total, or all of the combinations of anything, basically all the combinations in numbers in an array, for example, with a lot of for loops. So that's basically it, and then you print them out, and yeah, simple as that. Now at first glance it may seem like too complicated code. It's really just, once you get the hang of it, once you get what's happening, you know, the first number starts from 1 and goes to 44. The second number is always different than the first, that is, it's one larger and goes to 1 larger. This is 1 larger than the last, and goes to another larger, and so on and so on. Okay, so this thing could probably take a very long time, and it takes a long time not because the computer can't calculate all of these, can't make the loops, but because printing to the console works pretty slowly. So this printing to the console is very slow. You can see what happens. Now I'm going to do a live zoom. See what happens, you know, it's too slow. You know, we're generating the numbers as fast as we can, but the console itself is too slow. So what you can do, is comment this out, and we have a counter over here which is increased every time, and we just print out the counter. Look how fast this is going to happen. Ready? Now, pretty fast. That's the number of all the combinations. So these loops, looping through this number of numbers is pretty fast, unless you print to the console, which is pretty slow while printing. Again, if you do the same thing with redirecting the console, it's going to be pretty fast, and it's going to print them all out in a text file. Well, not as fast as just printing out the number of them, but still pretty fast. The file system is much faster than the console. Okay, so that's a lot of for loops nested in each other, and that's the example for nesting a lot of for loops. Yeah, obviously. Okay, so finally, if everyone bears with me long enough, we reached the end of this lecture, and in summary, what did we do? Well, we discussed C# loops and loops in general. Now, all these loops have equivalents in other programming languages. Basically, while, do while, and for have equivalents everywhere. So, but they're basically the same in C-based languages and in Java and in JavaScript. They're the same thing. They work the same way. Now, the for each loop, it's in some languages, it exists in some languages, not in all, not in the same way, but we discussed already what it is. We discussed that the while loop and the do while loop operate just on a single Boolean condition, that the while loop first checks the condition and then executes, while the do while loop first executes and then checks whether to execute again by checking the condition. We saw that the for loop is a sort of a loop on steroids. I mean, a loop which has more functionality embedded into it, like counters, like update statements, and so on, which can also be achieved. You can achieve a for loop with a while loop, but it will be a little bit harder, and it will be a little bit messier. So for things that excessively use counters and indexes and things like that, for loops are pretty convenient. We learned about the fact that the update statement for the for loop is actually executed at the end of the iteration of the body. That means at the end of the body itself of the for loop, not at the beginning. We saw about for each loops, as we said. We saw that nested loops can implement complex logic by implementing loops on each piece of a set. For example, like the one we had for getting all primes in a range, where we used a previously implemented loop to use in another loop, to nest it in another loop, and to get all prime numbers in a range by going through all the prime numbers and checking with the inner loop. And we saw continue, breaks, and goTos. We said that continue and break is probably the most often used. Continue is still used, not as much as break. We said that we should try to avoid them and try to write good loop conditions, but if the loop condition would suffer from not using the break, then we probably should think about using it, or think about restructuring the program itself. We said that the goTo statement can be pretty harmful, and you have to watch out for it, and our advice is don't use it at all, at least in high-level programming languages like C#, C++, Java, JavaScript, and stuff like that. There are other ways to go around it. If you find yourself really needing to use a goTo, then there's probably something wrong with your program or with your programming style. So think about that. Now, goTos, I'm not sure if we said that, but goTos are basically the way that loops are implemented. So while, do while, and for loops are loops that are implemented at a lower level through goTo. Basically, they go to their beginning, but that's on a lower level, not on a higher level. For each is implemented through a for loop, basically. Okay, so that's what we discussed today. Can't really ask you for questions because you ain't here. So if you have any questions, we'll be happy to try and answer as much of them in the comment sections below. So ask away. And we have some exercises which you can try. They're going to take some time, but that's the only way you learn to program. This is not literature where you can read books and learn about books. You can learn about programming, but you can't be a programmer without actually programming. So try the exercises. We'll try to add descriptions, and we'll try to add links to the materials, all the materials in the description below. So you can download these PowerPoint presentations, the demos and stuff like that. And I will go through each of these pages of exercises, so you can pause the video at any time and look at them from here if you wish, because I'm not sure if we'll be able to provide good enough links to these things. So pause anytime when you feel you need to, if you want to solve these tasks. 4 pages of tasks. I think this is the last one of them. So no, 5 pages of tasks. This is the last one of them. This is the one which I told you about, determining how many zeros does a factorial have without using big integer, or without even calculating the factorial itself. So think about this one. Ooh, 6 pages, sorry, 6 pages of exercises. Well, you have enough. If you've been watching the 2 hours of this video, you have enough time to solve these tasks. Okay, so that's it from me. Thanks for stopping by, thanks for listening, and have a nice day.